As is evident, though, our developers stay busy, innovating to build the next version of Jump for you. For the last 18 months, they've been working on Jump 18, and today we've got a group of them who are excited to share what they've been up to. Another person who's been busy writing code as a developer is our co-founder and chair. Please welcome, here to unveil Jump 18, John Saul.
Welcome to Manchester, the city of the worker bee. So, I'm excited to tell you all about Jump 18 with my other co-speakers. But before we go into the details on Jump 18, I want to pay tribute to a developer in Jump that pioneered many of the features in what Jump is best at, and that's design of experiments, DOE. And of course, I'm talking about Brad Jones. Now, Brad retired last summer after 25 years of Jump, 25 amazing years of Jump. And he led the development of DOE, the design of experiments features in Jump, and he was a true pioneer and a close partner with many other leading DOE researchers. So DOE in Jump is best in class. We were real pioneers and remained as pioneers. And Brad Jones first developed custom design, where he uses the power of the computer to create the best design for your situation. Then he innovated in Bayesian D-optimal, and it's used in supersaturated designs, when you don't have enough runs to estimate everything, but at least you can find the big effects, and that's what screening is all about. Also a pioneer in split plot optimal designs, when you have hard to change factors and you have to structure the design a little bit differently and estimate it differently. Also a pioneer in alias optimal and definitive screening designs, when you don't have enough runs to estimate interactions, but at least you won't have hidden interactions bias your estimates to the main effects, and also can estimate curvature in small screening designs. And more recently with Go SSD designs, group orthogonal supersaturated, and mixed level. These are variations on these Kronecker product designs of Hadamard matrices and fold-over conference matrices. That's a detail. Anyway, Brad Jones has an amazing list of honors. He was fellow of the American Statistical Association, and he had quite a trophy wall in his office of lots of other awards. So that is Brad Jones. But Brad was also good at recruiting talent, and so we have a great team still concentrated on DOE and reliability, that team now led by Ryan Lekovitz. Okay, now on to Jump 18. And I've kind of selected 5 or 6 feature themes, and they all start with the letter P. So we get people, pipes, presets, profiles, and Python, and people. And so I'm going to talk about the profiler. That's about cross-sections of fitted surfaces. Ryan Parker's going to talk about peaks, especially of interest to chemists and functional data analysis explorers. Mei Shen is going to talk about Jump Clinical and Jump Genomics. That's the people. Eric Hill is going to talk about pipes, that is data connectors and Jump Live. Paul Nelson's going to talk about Python, the language that connects to much of the world. And Julian Paris about presets, which is a little like preferences, but much better. So now about a feature introduced way back in Jump 3, the profiler. And let's bring up a data set. This is a classic data set from the Box Hunter and Hunter book. It is about modeling yield as a function of 5 other factors. And of course, when you first bring it up, it has, I've specified all the interaction effects, but a lot of these interaction effects are inactive. And so the best thing to do is just remove those effects that are pretty minimal, and that helps improve the stability of the predictions. You know, you shouldn't have a ton of parameters, especially in a small data set. But when I try to remove it, it says, shall I remove all the ones I selected or only the non-contained effects? And we recommend non-contained effects. So stir rate would have been removed, but it participates in the interaction, and the estimates are much more honest if you include the main effect, if you're including an interaction with respect to that main effect. And so this fits pretty well. And of course, I'm going to talk about the profiler, which is down here. And there's the residuals, and there's the profiler, and I can make that look big. And here we see the profiler is a cross-section of the prediction surface. And so given other factors constant, if you move one factor across its range, that's the prediction surface for that. And of course, if I move where the factors are constant, that does the cross-section at a different place. And so this is a good way of getting a quick look at the prediction surface and what factors might be important. Now, this profiler is shown with confidence intervals, but these confidence intervals look very, very tight. And if you look at the residuals, a lot of these residuals are, 4, 5, 6, and so on, but the confidence intervals are much tighter. They're about a little over 1. So if I go from a prediction of 65.4 to 66.5, that's a little over 1. But these residuals, they have a standard error with standard deviation of 3.2. That's root mean squared error. And so really, the residuals really vary a lot more than these confidence intervals. Why is that? Well, these confidence intervals are not about individual predictions. They're about the expected value, the fitted surface as a whole. And so these really measure what you want to measure, especially when you're screening factors. What is the slope significantly different from 0? And does it significantly affect the response? And so it would be nice if we could also have prediction limits as well as confidence limits. And in JMP 18, that's been added. And so I can add prediction intervals as well as confidence intervals, and those are much wider. If you thought that what we had before was prediction intervals, that's not what we had, but now you can have these prediction intervals on request. Now, can you get these prediction intervals when you save formulas to a data set? Well, let's look at the save command. If I save columns, prediction formula, right under that is save prediction interval formulas. And that's, with one command, going to save lots of formulas. And if I look at the data set, it's got that prediction formula. And then as hidden columns, which you can see over here in the columns panel, there are all these upper and lower confidence limits and upper and lower prediction limits as hidden things that you can express if you want. And now if I go and use these formulas, I can also get the profiler. And here's the launch platform for the profiler, and you see something different here too. It's much simpler than it used to be. The only things that are valuable to choose here are formula columns. So it only shows the formula columns instead of all the columns that you can predict from. And so that's the formula column I want. But what about all the formula columns for the confidence intervals? Well, those are automatically chosen. So if you choose the prediction column, it automatically looks through the data set to see if there's confidence intervals and prediction interval formulas, and that includes that as well. Also, used to have a role for noise factors. That's still there, but you specify that through a checkbox, and then it prompts you for the noise factors, prompts you only for factors that are involved in the prediction formula. And so now we have the profiler using the formula columns. Let's make this a little bit bigger. And since we have formula columns for the prediction intervals, we can include those too. Okay? So wouldn't it be nice if you could have the data points shown in here too? Well, there's a new option for that called data points. This is one of the two big things that Zan Gregg implemented, and I'll show you the other thing in just a minute. And here you see it's a designed experiment, so all the points are at the extreme ends. If you have happenstance data, it looks a little bit different, observational data, but with X's as a designed experiment, all the points are at the extremes, and you can see these points here on the ends of the factor space. And, but look, these these points really are far away from the prediction things. So how can they be data points for that prediction surface? Well, the problem is that a given point might be, let's select one of those points, row 1. And row 1, represents values for all 4 factors shown here, and yet it doesn't, the line of fit doesn't represent what those factors are for that. Now, if I change the factor settings to where the settings are in row 1, which I can do with this command, now row 1 is fairly represented in this. So you can see where all the other factor settings are for all the data points, but only the ones that are highlighted here are representing the real fit because they're close to the current values of the profiler. And every time you change the value of the profiler, it changes what points are close to the others, and the others are dimmed, so you know that they're not fairly represented as in their prediction space, but they do represent the data from the experiment, okay? And you can see how that works. There's an animation feature under factor settings. You can animate it, and I'll animate it for data sequential, and now you can see that for each row, it's selecting different near points that are represented near that same row's factor settings. And it shows you that all these prediction surfaces are changing. And notice that some of these slopes are changing dramatically, temperature, for example. And that's because temperature is interacting with 2 of the other factors, concentration and catalyst. And in fact, if I, under certain values, I can make temperature look like it has no effect on the response, and that's because there's a hidden interaction here. In fact, you might even want to set it at this point, if you want it, you might even want to set the other factors at those values if you want it robust, want a solution that's robust to temperature, that's less affected by temperature. So interactions can help you there for robust process engineering. But wouldn't it be nice if you could see the interactions? Right now, you can't tell if there's interactions without moving things around, okay? But Zan added the other feature called overlaid interactions. And with that, you can see that it shows where that line of fit would be, that profile would be, if you had changed factors to other values. And there's several ways of doing that. And so if I look at this line, that's where concentration, if you change concentration to 3.3, it would be that line. And now you can see those interactions dramatically. And in fact, if you're curious about what values relate to that, you can just go over the hover help and click on that, and it will change the other factors corresponding to that. And so now all of a sudden, you can see interactions in the profiler, you can see data in the profiler, and the data that makes sense for the current factor settings. So we have the profiler, almost 30 years old in JMP and still growing up, with prediction intervals, data points with dimming, overlaid interactions, used in 129 different contexts in JMP, actually interactive in JMP Live, and extended in other ways, like the Design Space Profiler, which was new last release. And there's a blog that Mia and Zan and I wrote on the prediction profiler enhancements in JMP 18. So now Ryan Parker will show peaks.
Well, thank you, John. I'm excited to be here today to share with you the new tools that we've added to the Functional Data Explorer in JMP Pro 18 that are going to make it easier to work with peak data. We have a variety of peak data that we want to consider. For example, in chromatography, where we have an interest in trying to separate compounds, such as in pharmaceutical applications, where we have a goal of trying to identify where the peaks are located, how how their heights are, their timings, and construct various summaries of them. We also have spectroscopy data, where here the peaks are representing the underlying components, and we want to be able to understand these components. But we can also think about some non-traditional peak data, where maybe you're at a theme park and you want to know when the best time to go wait is, where the peaks here are representing the longest times to wait. So the first tool I want to show you is multivariate curve resolution using this carbohydrate spectroscopy data. So these data are made up of a 3-component mixture of fructose, lactose, and ribose. And the peaks you can see in these component functions, they're kind of identifying these different components. So our goal is to estimate not only these component functions, but also some mixing proportions that were used to construct the spectra that we actually observe. So to launch FD in this case, we have a data set where all of our rows are considered a function and all of our columns are the timing variable. So we go to the Analyze Specialized Modeling menu to launch FDE and choose the rows as function option. And since each row is its own function, we don't have to specify an ID, and we just drag over all of our columns to represent our output. So once FDE is launched, we'll find the multivariate curve resolution option under the Models red triangle menu. So we also have an unconstrained multivariate curve resolution. This is for if you want to allow negative values in the component functions. The kind of standard MCR is going to just use positive values. So if you're not familiar with FDE, kind of the main goal of the platform is to take the variability in your functions and represent it into a smaller subset of shape functions. So in multivariate curve resolution, these shape functions should ideally represent the components of interest. And so the estimates we have here, you can see that they're matching up fairly well. So shape function 1 is representing fructose, shape function 2, lactose, and 3 with ribose. So along with a shape function, we're going to get functional principal component scores. In the case of multivariate curve resolution, these component scores are representing these mixing proportions. So when combined with those shape functions, we're going to be able to approximate the functions that we observe. So we can kind of see how well is it doing in this case. So when we have 0 truth values for these mixing proportions, we're going to be estimating small numbers here. And similarly, where we know that we're getting the full component, we're going to get it estimated to have large mixing proportions. And a similar story holds for the other components here. So once we have these summaries, we can save them out, save the shape component functions, save these mixing proportions to go to further analysis and jump. So I also want to mention the other new modeling option that we have under direct models called the penalized SVD. So the main thing we're getting here is allowing us to have easier to interpret estimates by being able to pin things to 0. Just kind of using the other data set, or that carbohydrate data as an example, the biggest thing to point out is you'll start to see zeros in some of these principal component scores you'll estimate to make it easier that you know that, okay, that's not involved. And that's kind of where the penalized SVD comes in. So finally, I want to cover another new tool that we've added called peak finding. So in peak finding, we are trying to either by hand or with some automatic tools that we have available, identify the peaks in these data. In this data set, we have 2 primary peaks of interest. Some of the functions have kind of this initial, almost nuisance peak that we don't want. And our tool is going to allow us to find these peaks and to summarize them with things like area under the curve and resolution metrics for these different peaks. So we have 10 runs of this experiment using various combinations of our flow rate and temperature for these batch IDs. So when we launch FD in this case, we'll use this Models red triangle menu option again to launch the peak finding interface tool. So when you first launch it, you'll be presented with a large display of each individual function that you can toggle through. On the right, we have an editor option where you can add or remove a peak by hand. We have edit boxes so you can change the IDs of these peaks, where they start and end, and their locations. And we also have a tool to perform automatic peak detection with the continuous wavelet transformation. So I want to show you just kind of how this tool works. So we use automatic peak detection by default. This first function, we don't separate the peaks well, so we'll go ahead and just remove the peaks there. And now we'll cycle through and find any of these functions that have kind of that nuisance peak that we want to get rid of. We also have sliders here that you can change the bounds of these peaks if you feel like they've been estimated kind of too wide. But we'll go through and we can remove these. And once we're done removing them, we can go to a multi-view where we'll see all of our functions together. And now here we can see that this peak ID 0, they're all matching. We can go to the table, select the row for peak ID 1, and now verify that those are all kind of lined up where we want them, so we know that we're ready to proceed with our analysis. So with peak finding, we're going to get a lot kind of richer set of summaries kind of associated with potentially many, many peaks. Something very simple is how many peaks do we have in these functions. So that first function, we don't have any at all. We remove them, so we're not going to get any other summaries associated with that one. But we also have area under the curve metrics that we understand are very important. In addition to having those, we also know that being transparent with some of these measures is important. So we're simply calculating these with a trapezoid rule over the observed data. And we also have half height widths and their associated resolutions. So you can think of the half height as being, how wide is the function where your the values are half of the total peak height. And with those, we can calculate resolutions between peaks. So if we're unable to find, like if we have some overlap in peaks, we're unable to find these half height widths, you'll get a missing value, in which case you'll also get a missing value for the resolution. But when we have them all available, you'll get that resolution metric. So we can save these summaries kind of like we do in other parts modeling areas of FDE, and we can build some simple linear models. So here I built a simple model using the flow rate and the temperature so that we can know, kind of get an idea of how are these impacting our summaries that we have. So we can see that higher flow rate and temperature tend to be associated with better resolution of the peaks, and also lower flow rates are tended to be associated with a larger area under the curves of these peaks. So our hope is that these tools that we've added, they're going to help you more easily gain insight from the data you have, where you have peak data. And with that, I'd like to turn it over to Mei-Chen. Thank you.
I'm Mei-Chen from the Life Sciences Group. Today I'm going to talk about some new features related to people. So my group focuses on clinical and genomics research. JMP Clinical is a focused product that for clinical trial data review, and it's utilized worldwide across pharmaceutical industry by drug sponsors and regulatory agencies. JMP Clinical focuses on safety review, medical monitoring, and study monitoring. It's now fully based in JMP with many improved features. We can also explore genomics features in JMP Pro, from easy data importation to fast and automated workflows and platforms. And there are plenty of Ps in JMP Clinical, for example, patient recruitment, perfect scheduled attendance, patient profile, and there are many new features available in JMP Clinical 18, including the tools like data mapping tools, clinical recorder tool, and many reports like the risk-based monitoring report, the drug-induced liver injury report, and more. So all drugs must be evaluated for the toxicity of the liver. Drug-induced liver injury, or called DILI, is one of the most prominent and serious adverse outcome of a drug product. The FDA guidance for DILI says most drugs withdrawn from the market due to hepatotoxicity have caused death or transplantation at a rate of less than 1 per 10,000. This means that a single case of such an event is unlikely to be found. And that's why we have our DILI report here, which is a comprehensive review of all the clinical trial data that's related to DILI. It identifies all subjects that show signs of DILI and gives us a whopping 25 figures and tables. including this very important screening plot that indicates subjects who potentially experience the DILI, and this Sankey diagram that allows us to explore the post-baseline migration of the labs. Then based on this screening plot and its 3 quadrants, namely the potential highest law, cholestasis, and tempos corollary, we can derive specific summary tables, like here. And we provide shift plots of peak versus baseline for enzymes of interest. Then based on all of the above figures and tables, we give a list of subjects with DILI. So in sum, this DILI report comprehensively covers all the critical FDA and customers requested tables and analysis. The other new feature available in Clinical 18 is the risk-based monitoring report. The purpose of this report is to help organizations that conduct clinical trials to detect data quality and patient safety risks at an early stage. So the risk indicators can be related to patient enrollment, disposition events, patient safety, and overall risks. So when data is available, these risk indicators data tables can be generated at site level, country level, monitor level, vendor level, and subject level. Within a specific level, users can use this local data filter to look at a specific subgroup of interest. You can also define and change the risk thresholds and explore more from here using the generated data tables. So if you have clinical trial data, please try this. And next, let's explore some new genomics features in JMP 18. So we have automated the very popular JMP genomic basic expression workflow using the modern JMP workflow files. The workflows give you the power to view, visualize, and analyze data at each step. You only need to configure the data table names at several parameter values at the beginning and then run the whole workflow. And this basic expression workflow consists of 8 steps, including the distribution analysis, correlation analysis, principal variance component analysis, data standardization, and ANOVA. From the workflows, you can see we can generate those beautiful heat maps, parallel plots, volcano plots, and more. We also have more workflows for single-cell next-generation sequencing data and other omics data. So in JMP 18, we enable more genomics data format importation, including the binary files and HDF5 files. And currently, there are 3 genetics platforms available in JMP, including the marker statistics platform, the marker simulation platform, and the marker relatedness platform, which is just added to 18, and even more are in the works. The marker relatedness platform estimates a variety of genomic relationships between pairs of individuals. And let's look at a practical example involving rice genotypes. So imagine we're investigating the relationship between different rice populations and the resulting grain yield. We also have genotype information, such as the SNPs columns. So we know that some samples can be related genetically, especially when the sample size is large. So it's crucial to recognize this potential relationship structure within the data, so later we can fit more advanced statistical models and adjust for this genomic relationships. So let's go to the new platform, marker relatedness here. We want to specify all the 8,000 SNPs into marker. And here, instead of using the trivial Pearson correlations, we provide the genetic-specific kinship measurements with the identical by state, IBS, being the default option. So by running the platform, we can derive the distribution of the kinship measurement, the PCA results, and clustering results for the samples. We also derive the square relationship matrix, or call it a kinship matrix. And back to the report under the red triangle, we provide this option called merge kinship table that allows us to easily merge this relationship matrix back to the original data table for easier downstream analysis. So this leads to our other new feature for genomics, that is we can fit very fast mixed models for genomics data. So specifically, we can fit two types of models, the ridge regression blob, or called RR blob, and the genomic blob, or called G blob. Both models are used to estimate the genetic merit of individuals using marker information. And they are both widely used in animal and plant breeding. So how fast can we fit those models? Let's go back to the example. And we can fit RR blob model under the fit model platform with response screening personality. And here, let's specify the outcome and the fixed effect. Now, here, I want to specify all the 8,000 columns as the random effects. And we introduced this new feature that's called grouped regressors. The grouped regressors feature allows us to set a group of columns to a common variance component. So let's run the model. And our blob model finished within a second, so it's really fast. And we derived our blob values here. So similarly, we can fit a G blob model with a kinship matrix, also using the fit model platform with a response screening personality. So if you're interested, please visit our website and learn more. Okay, next I will hand it over to Eric.
Thanks, Mei Chen. I'm Eric Hill. I work in the Jump Live team. I was assigned the topic of pipes today. In my research on this topic, I found that there are basically two kinds of pipes. They're the kind that you smoke and the kind that you use to convey some material from one place to another. I'm going to be talking about the boring kind. Now, JMP is a data analysis tool. Can you think of anything about data analysis that might require conveying something from one place to another? The data, right? You've got data in a relational database, it's an Excel spreadsheet, something. You've got to bring that data into JMP so that you can analyze it. Anything else about data analysis that might need to be conveyed from one place to another? Nobody? The analysis itself. So if you've discovered something amazing in JMP, you want to communicate that with other people in your organization so that they can make decisions and have the same insights that you're having. So that's another place where we may need to convey something. First, we're going to talk about the data pipe. We've had data pipes in JMP for a long time. Back even in 16 and earlier, we had text import and Excel import wizard, and kind of the heavy lifter was ODBC to go get data out of your relational database and bring it into JMP. We found about that time that there were some data sources coming along where ODBC was not a great fit for getting the data. A great example of that is the historians, OSI Pi historian in particular. So in JMP 17, we created or released the OSI Pi historian data connector that rather than ODBC, it uses the OSI model itself, the OSI API, to get data, which is a much more effective way to go about that. In 18, we continued to enhance the OSI Pi historian connector, and we're releasing an initial set of what we're calling data connectors. It's really a framework in which we hope all of these disparate data connectors, kind of an umbrella for all these over time. Now, most of the ones we've released in 18 are still wrappers around ODBC, but we plan to be working on other more customized data connectors, for example, for Snowflake, that will be better for those kind of situations. This is an example where I'm using Query Builder. It comes up in a second here. And this is just a query builder that uses the PostgreSQL data connector. I'm going to just run it. Here comes the data. I'm going to show the source script, which we put in our data tables, that shows that it's coming from a data connector. It's a little less verbose than it is with ODBC, so that's kind of nice. That's absorbed in the data connector. And then I'm going to run a quick analysis because the purpose of getting data is to analyze it, so we're going to do that. The main point here is that sort of the workflow for data connectors will be very similar to the workflow you're used to with ODBC and other data sources. So this is our first pipe of the day. We've got databases and historians, and we're using ODBC and data connectors to get that data into JMP. Now, what about the analysis? Here's the analysis that was on the previous slide. There's some interesting things here. This left-hand graph looks a little bimodal there, so something weird's happening there. And in the right-hand graph, we've got a critical ratio that seems low. So I would like to share this with colleagues in my organization so that they can, to bring it to their attention. So here it is sitting in my desktop on JMP, and here's all these other people in my organization I want to get this to. Some of them may have JMP, but some of them may not. How am I going to get that to them? Well, the answer we believe for that is JMP Live. JMP Live is a separately licensed web application that you install behind your company's firewall, so nobody can get to it except people in your organization or people you designate who you want access to it. And it allows us to publish a JMP report and the data that goes with it up to JMP Live, and then anyone in your organization who needs to look at it can see it, and they don't have to have JMP, they just have to have a web browser. And it's not just a snapshot they're looking at, they can interact with it. I have an example of that over here. Here's that analysis I just showed. I've actually published that to JMP Live. So within JMP Live, I can still use the data filter, for example, and I can see that this Macmillan supplier seems to have the high concentrations. People can see this critical ratio over here. Something else you'll find in here is that a conversation is taking place with respect to this analysis. Under the comments for this report, this person at the top here has @mentioned some other people in their organization. @mentioning is a way to call people into a conversation that may not have otherwise noticed that this got published. Now, this is a brand new feature of JMP Live 18, and we think it's, you probably use it maybe in the community or other social media platforms, but we think it'll be a great way to draw people into conversations and have those conversations right alongside the analysis that you're looking at. Now, after a couple days or a week, if people start working on this and starting to improve the problem, more data is going to be generated. I would like for my report to reflect new data that comes along tomorrow or next week. How do I go about that? Well, in JMP Live, we have a feature called scheduled data refresh. It's just data refresh here, but the scheduling is important. What that means is I can have a script running in JMP Live that will go get my data and get the latest version, and then my reports will automatically generate. Here's an example of that. Here's some data in JMP Live. Here's the script for it, which usually just comes from a source script from your data table. And then there's a schedule here. So at 9 a.m. to 5 p.m. every 2 hours, Monday through Friday, this script is going to run, go get refreshed data, and update the analyses so my analyses stay current with whatever the latest data is. Here's an example of that. It's 12:59 here. You might be able to see at the bottom. When that clicks over to 1 p.m., in America, that's what we call it, the data on the left will regenerate or will refresh using that script, and then these two reports on the right depend on that data, so then they will also regenerate. It takes just a second here. So there they go. So I can just constantly have my analysis reflect the most recent data just by putting that script in there. All right, now I said earlier that anyone in your organization can see the data or the reports that you publish to JMP Live. But it may be the case that not everybody should see it. Maybe it's sensitive data. You want to restrict who can see it and who can't. Well, JMP Live has those tools. It's always had a way to create groups and to give them permissions in certain parts and spaces in JMP Live. But it was kind of a manual process. I can pretty much guarantee you that back at your company, somewhere in your IT, there's an Active Directory or an LDAP server that knows about every person in your company, and it groups them, to divisions and departments and other ad hoc groupings of people that your IT department uses to give people access to different services that IT provides. Wouldn't it be great if we could just take that same organization into JMP Live? Well, it turns out in JMP Live 18, we've built that pipe. So now you can select, you don't have to bring everyone over from your Active Directory, but if you have groups or divisions that you know should be on JMP Live, you can select the ones you want and just import them using this synchronization feature, And they'll come into Jump Live, and they'll be ready to go. You're ready to start having those conversations and ready to give people access. So it gets Jump Live to feel like a part of your organization much more quickly than previously. So that's our last pipe there with the Active Directory syncing over into Jump Live. So to sum up my presentation, if you want to get the most out of Jump, your investment in Jump, make sure you're using all the plumbing. So now I'm going to turn it over to Paul Nelson, who's going to talk about Python, but not the snakes. It's something else. Paul?
Thank you, Eric. Paul Nelson, and I'm here to share with you. I'm excited to bring forth all of the work we've been doing on the Python integration since Jump 17. Design thoughts that I've had. I want the Python integration to just work. For some of you, it worked fine right out of the box, but for all too many, it was a real challenge to make it, to configure it. Not only that, with the Python, you have, different versions of Python on every desktop. The scripts couldn't count on finding the same version of Python. We've now embedded Jump 18 carries an embedded version of Python, Python 3.11. It's installed with Jump. That allows us to have a tested and verified environment. We know it works because you're going to use what we've been using. Then, it'd be nice to have an inviting and productive Python environment. And to me, that means a script editor that's Python aware, code coloring, being able to run your Python scripts the same way you run the JSL, being able to run it from the script editor, good integration with the embedded log and the log, actual real good diagnostics coming back so you can track down your errors in your scripts. And while we're at it, wouldn't it be great to be able to have live access to your Jump data table from Python, to be able to create a data table from Python, to be able to add columns, add rows, be able to read your data table or modify those values directly from your Python scripts? Well, that's exactly what we built in Jump 18. Further, we've added a new Python category in the scripting index, which allows you to see all of the help and examples for. We've created an import Jump package that you'll use from your Python to be able to get at Jump's internals, what we've opened up from Python. We've also added a scripting, in the sample scripts, there's a Python directory carrying a bunch of example scripts. Further, we want to be able to easily extend Jump with additional Python packages. Jump does a whole lot, but there's an awful lot there that's available from Python. And it's the Python, think of the Python as a peer to JSL, not a replacement. So let's get to the fun stuff. So here in Jump, we'll go with the Finder, we'll go with the scripting index. So here we have a Python category. And we've got all this laid out, data table, object, column object. One of the better examples to show a lot of what we've done is a run JSL example. Just as you could run Python from JSL, you can now run JSL from your Python scripts. This also provides us kind of a backdoor for things we haven't yet implemented in Python. You can call the appropriate thing from JSL. Our import Jump package, you can create a data table, set some of the properties, create columns, new column. We can fill those column values. Here, this one would give us a missing value because it's a numeric going into and then we can set the individual cell. And notice it's column row, and it's, as for with Python, it's zero-based indexing. So we can run this script, and we created from Python a two-column table, a character and numeric, and then we use the run JSL command to format the columns. So next, we'll go with Jump opens a lot of data file formats. One of the more frequently asked for is Parquet that we haven't supported internally in Jump. But with the PyArrow package, you can load a Parquet file. And Jump now, because you can access the data table live, we don't have to go through pandas. We can create our own little function that will take the schema from the Parquet column, build a Jump data table column, and then it's as simple as iterating through the columns that you want, adding them to the Jump data table. Again, using the run.jsl to set some of the column formatting, and then some print statements here down at the bottom, dumping out the Parquet schema. And I'll run it with the embedded log. And we just took a 1,000-line Parquet file, 1,000-row Parquet file, and created a Jump data table from that with formatted time, salary, and data had a missing value as well. Modern laptops and desktops have GPUs. They're powerful, and not being able to utilize them leaves a lot of horsepower behind. The Mandelbrot example here uses open compute language that lets us run code on the GPU. Python has a PyOpenCL package, which utilized here. This example creates a 2K by 2K Mandelbrot fractal. If I run it on the CPU, it takes over 16 seconds. 2K by 2K in the fraction of a second. We can see that in the log. This time I didn't use it. It took roughly 4/100ths of a second on the GPU rather than using the CPU. And the last example I have is Jump has a lot of powerful statistics. But let's say you want to use one that Jump doesn't have, such as density-based clustering or the newer hierarchical density-based clustering. So we've got an HDB scan example where we import the HDB scan package. Here we're going to take a Jump genomics data set. And here we're going to create a pandas data frame from our Jump data table. And you can notice we also support the slice syntax from our columns, and it's column row. So we'll take 60 columns from the data table, we'll do the clustering, and then create the hierarchical output. And we'll also run the embedded log on this one, run script. So we wrote the genomics data set in our embedded log. Yeah, we've got the cluster output results. And we've got the graphic. So, recap. We want to make the Python integration just work. It should just happen for you out of the box. It should work, and most of those configuration issues should now be gone. Make a productive and inviting environment within Jump, and easy expansion using Python's packaging capabilities. And there's much more to come. Thank you, and I hand it over to Julian to tell you more about presets.
Thanks, Paul. Good morning, everyone. I am so excited that I get to be the one to show presets to you. I think it's going to really make your work feel more streamlined, and you're going to be able to get a lot out of it right away. So I have just two objectives for the next 15 minutes. The first one, teach you everything you need to know about presets to be more effective in Jump. Now that sounds kind of ambitious, but I think most of what you need to know, you actually already know. Presets are going to work really seamlessly in how you already use Jump. The second objective, and I apologize, this is a little selfish, I need to settle a bet I made with my partner Margot, and I need your help with this. So I'll get to that first, actually, because the disagreement that brought this up is going to be the data set we're using to look at presets. And the disagreement comes about from this question. Who's the Hermione Granger of Star Trek: The Next Generation? So this is how nerdy this talk is going to be, so I think this is the right crowd, but I'm trusting you to get on board with this. Okay, so if you don't know, Hermione Granger is from Harry Potter, Star Trek The Next Generation. So we were discussing this, and my answer, here I am over here, Wesley Crusher. This feels obvious to me. Wesley's brilliant, he's young, he's ambitious. I think that's the right answer. Margot, she's over there, her answer was Jean-Luc Picard. By the way, I didn't just make this for the talk. She was needing it for one of hers, so I'm not that nerdy. But as she said about Jean-Luc Picard, you know, Gryffindor energy, but actually a Ravenclaw, which is also a hot take on Hermione Granger. But that was our disagreement, and we needed to answer this question, so of course we had to pivot to some data. Oh, I wanted to show you pictures of the characters, but for copyright reasons I can't. So here's my take from AI. We have Jean-Luc Granger and Hermione Crusher. So just keep those in your head. That's who we're trying to decide between. So to answer this, I went looking for some data. The Open Psychometrics project has this incredible data set, which I'll share with you all, which is data from basically millions of people who are making personality ratings of fictional characters. So here I have about 800 rows, 800 characters, and people have rated them on things like calm to anxious, biased to impartial, deep to shallow. Incredible data. So we're going to be able to look through and do some statistics to find out really closeness and multivariate space between characters and answer this question once for all. Before we get to that, let's explore some presets. And presets, being called platform presets, obviously are going to show up in platforms in Jump. So let's start off with a platform that I always start with, distribution. And I'm just going to take one of these columns. We'll do competitive to cooperative. And we'll get the default distribution output. Now, platform presets are all about the purpose of the platform. Of course, you can set a preference, and you've seen I've set one. This is stacked output. But we have different purposes for our platforms, depending on the day, depending on the application. So right now, I'm trying to show you some data. So I'm going to go to the platform preset menu. It's at the top right of your platform. And I'm going to go to a preset I've already saved, this simple black and white. And the platform is going to reconfigure itself with all the customizations I made in the past, but now I can just apply them with a single click. So this preset includes some extra axes. I've changed the color of the bars. I've even moved the summary statistics to the right. And so this makes it in a way that I can copy and paste or even show pretty easily. And so a preset is around a purpose, again. And if you look under the presets menu, in lots of platforms, we even include samples that kind of get at some of the purposes you might have for a platform. For instance, I can do this check normality preset, and that'll reconfigure the platform to have applications for checking the normality of a distribution, including producing output, the goodness of fit test, things that you might spend some clicks on, but instead you can get to with a single click from a preset. All right, let me go back to the simple B&W. Now, I want to make a note. Presets are not about the column. They're not even about the data table. In fact, I can open up a different data table. This is 120 years of Olympians history. Also a cool data set. Let's look at the distribution for age. Notice that I have the same presets available here. I could toggle right into the same simple black and white. And this is the identical output. So everything in that preset is applicable because it's the same platform. So I can hop right to the end. So presets are not about the data table, they're not about the column, but they are about the platform. And to show that, let me open a separate platform. I'm going to do fit y by x now, where this is an environment, obviously, it's going to be different than distribution. Different options are going to be available. So let's set this up. I'll do competitive to cooperative, and let's do kinky to vanilla, which is a humorous thing that people were making ratings of for these fictional characters. As you might imagine, Fit Y by X has different options, so different presets will be available. It doesn't make sense to apply distributional presets here. And if we look at the sample presets first, you'll see they make more sense. They're about things like correlation and summary statistics, or a linear model profiler. This is using the same points that we've added to a profiler that John showed. Right, so those wouldn't make sense in a distribution context because those options don't exist. So again, presets, they're not about the table, they're not about the column, but they are about the platform. All right, so let's, now that we've seen what a preset is, I'm going to go back to the platform launch, just revert it. So let's make our own, because I want you to see that you basically already know how to do this. Making a preset is not about any coding. It's not about going in and doing anything complicated. You're just going to set the platform up the way you want to. So for instance, let's make a presentation preset. Gosh, I'm using a lot of P's in this talk. And we may want to do something like changing the font sizes. And so I'll make this 24 for that. I'll do the same thing here. Let's do 24. I normally like to customize my axis fonts if I'm making a presentation. So I'll make that 18. I'll do the same here. And let's do some red triangle options too. I actually quite like having the histogram borders. I think that's a nice little edge of the graph. And let's say that this is done. Like, we love this plot, let's say, and we would love to make this every time we do a presentation. So let's save a preset. Preset menu, save preset as, and let's call this bivariate presentation. All right, bivariate presentation. So now that's a preset I can use somewhere else. Let's keep this over here. I'll go to fit y by x. Let's just arbitrarily take a few columns to look at. Put this over here. Under the presets menu, my most recent presets are up here, or I can go to the My Presets section. I'll turn on bivariate presentation, and there it is. Now I get to use that whenever I want to make this particular plot anytime into the future. So very cool. What if I want to change this? Like, maybe I wanted these graphs to be a different gray, so I'll do that. I actually quite like to take away the borders here, and so I'm going to take away that, and I'm going to take it away here, because this kind of lets the histograms fade off into the distance there. Maybe I want the size to be a little smaller, so it's not the entire screen. Let's just assume I'm done. Let's update this preset. Presets menu, save preset as. There's the replace option. It even has the last time I applied this selected. Hit OK. Let's go over here, apply, and we're done. In fact, so often is the case that you want to make changes in one platform and or in one window, I should say, and make the changes over here. There's actually a really fast way to do that. Let me just make some changes. Let's imagine you just want to make this plot like this plot. Grab the menu, drag and drop, and you can make them the same. Really useful, right? So anytime you make those changes, you don't even have to make a preset. You just can drag it over and make them synchronized. So really fast, it fits into your workflow. It's basically how you're already using Jump. Just save the presets if you need it. Right? Isn't that so cool? I will give Dan Shakori credit for that. He's like, you know, we can just make the preset menu draggable. And I'm like, yes, we can do that immediately. So amazing stuff. So now that we've done this, I just want to make some notes. If you have presets you want to share because you've built them and others in your company are like, that's really cool, I'd love to do that too, sharing the presets is really simple. Under the preferences, there's a whole platform presets section where you can take the presets you've built, export them to a Jump preset file, share them with your colleagues. That means they can make the same standardized graphs and reports that you've made. If you're a developer in your organization, and I imagine lots of you are the super users at your companies, you may want to bundle together a set of presets. You can do that too. Go to New Add-in. There's a Platform Presets section where you can take those presets you've built, bundle them, call them a name, Company Presets. And now when you distribute this, that'll be a source under the preset menu. So everyone can use the presets that you've actually distributed. And so for standardized reporting or for any kind of standardized analysis, this makes it really easy. And again, these apply to any table, any column, so you are using the purpose over and over without the context or without worrying about the context. All right, so we came here for a purpose for me, which is deciding who is right about which character is the Hermione Granger of Star Trek. We need a multivariate distance, and I'm going to do this in potentially a statistically dubious way, but it's fine. We're going to use hierarchical clustering, and I'm going to take attributes that we've measured here, a big set of them. I'm just going to label by the character. We actually don't even need the clustering, because what we're really trying to save out is the distance matrix. This is an 800 square matrix now. Every character against every character in terms of the multivariate distance based on that clustering algorithm. So I'm going to make a graph here, because what ultimately we want to do is see who is the closest to Hermione Granger from the Star Trek universe. So I'm going to do a couple of things. I'm going to drop the name. This is everyone in that data set. I'm going to pull up Hermione here, and I'm going to put her both as the color and the X. I'm going to do this as descending. So now the top person in this graph is going to be the closest to Hermione. I can hit done here, and I'm going to apply a preset I've done before. This presentation bar is no metric. It just drops the x-axis because we don't need it. And now we're going to local filter. I'm going to filter on the name, and I'm just going to do the people who are in the next generation. So just that Star Trek. I'm going to select these. Once I let go, that's going to change, and it's only going to show the Star Trek Next Generation characters. The top of the graph is the person who's closest. The bottom of the graph is the furthest. I have to tell you, I have not done this yet. Margot made me promise not to find the answer until I got up here. In fact, my co-presenters could even attest, in the practices, I was really cagey about what my presentation was, so they haven't seen this either. Okay, so we're gonna do it. Drop, and, oh no. Margot could not have been more right, and I could not have been more wrong, evidently, based on this metric. So again, if you're just looking at this is the distance to Hermione, and shorter is better. Gosh, I don't want to tell you what we bet, because it's not going to be good for me. So if I won, I was going to get to record a video up here, and I was going to ask you to cheer for me while I told her how wrong she was. Don't worry, we have a great marriage. If she were right, I'm supposed to record a video and tell her how right she was, and you're supposed to boo me? Can I ask you to do this, or be willing? Okay. It's going to be really bad. I am not happy about this. Okay, give me a second. I'll give you a signal, okay? And then you should boo. Hey, Margot, I'm here with everybody. We just did the analysis, and gosh, you were right. I was so wrong, and as agreed upon. Ooh, that was awful. Never do that to me again. No. Ugh. That's gonna haunt me. Thank you for playing along with that. She's gonna love that. To recap, platform presets. Build yourself a library of your preferred platform configurations fit for every purpose. Just as you're using Jump, if you find yourself repeatedly doing things, just save it as a preset. You can have as many as you want. You can delete them, update them. Just save for every purpose. This is going to help you create consistent output day after day, week after week, project after project, which is really useful just for your own work, but also if you end up showing data a lot, come up with a style that is yours, that you want to show data as, because then it's easy to make, but it's also just kind of personal branding. Finally, easily share those with people in your organizations, because obviously the work you do is similar often to other people's work. And you're finding that here, of course, but obviously at your organizations, you're going to find that you do similar things. I mean, in fact, it reminds me of Mark Twain's quote, history doesn't repeat itself, but it often rhymes. Like, our work day to day may be different, but it has similarities, it overlaps. And so if I can be so bold to update Mark Twain, I'm going to make us a version for us. Our analyses may not be identical twins, but they do share a family resemblance. So with that, I'll end. Enjoy, and I'll see you around the conference.
Thank you very much. To be clear, Julian is the Hermione Granger of Jump, so lest anyone doubt.
Take it.
That was all very exciting.